something goes up. So hi, everybody. I'm Zach. I'm a first-year PhD student working with Yupeng here in Dean Barrett. I think Yupeng is in attendance, so I'm sure he may have some questions for me at the end. But working in the computer-assisted navigation, diagnosis, and intervention group within CMIC and YSET of UCL, as Eugenio mentioned. So I'm going to be talking a little bit different than some of the other talks we've seen today. I guess a different way of looking at imaging for solving a registration problem using point clouds instead of the images themselves. So a little bit of background before getting into what we've done on prostate cancer, just as that's kind of the main application that I'll be talking about today. And it's the most common non-skin cancer in men in the UK, and it's also one of the most common cancers in most developed countries. And in the UK, about 1 in 7 men will be diagnosed with prostate cancer in their lifetime. And while there is no single test that we can confirm prostate cancer with, the higher risk patients, whether that's through testing or family history and things like that, they are likely to receive an MRI in the UK and in more developed countries. And if they do see things of concern in the images, then they'll often progress to a biopsy, which is often guided purely with ultrasound. And as you can see, you can all see my mouse. You can just see there's a cancer shown here in the prostate, and just to give you an idea of where the prostate is in men if you're unfamiliar. So these biopsies are performed often using only ultrasound. And if you look over at this image, where the white arrows are is actually showing where the tumor is, and to somebody maybe slightly or not terribly experienced with ultrasound, that might be quite difficult to see. So misdiagnosis here at this point in terms of the grading of the cancer can be resulting in unnecessary surgeries and lots of other complications if there are problems that occur in the surgery. So when we look at ways of trying to improve prostate biopsy, we can look at multimodality image registration of ultrasound, which is already used to guide the biopsies typically, and those preoperative MRIs that were used, and do something that's the clinicians will call image fusion, but as I think most of the people here would refer to as image registration, as was in the title. And so one use of this image fusion is for doing this kind of magnetic resonance and transrectal ultrasound registration in real time in the surgery. And so I'm just going to play this video, which is not mine, but I found on YouTube, and it seems to be quite helpful in terms of sort of explaining the topic. It seems to be a little bit choppy, but you can get the idea there. And so this kind of imaging, when we can use the ultrasound to register to the MRI, so that the clinician can actually use the ultrasound in order to view where they are in the patient, but use the MRI to sort of get some of that better imaging quality and identify the lesions with hopefully a little bit more ease. And so doing prostate biopsies in this way has actually been shown to improve sampling, improve patient management, so that we're seeing less unnecessary surgeries, and people are being monitored actively and actively surveilled if their cancers are not too high grade. Often these kinds of biopsies that are guided in this way with the image fusion require a full 3D ultrasound volume, as you could expect from watching this video. And there are some methods that do 3D MRI to 2D ultrasound, but they often require a little bit more extra work. So the question kind of then becomes, can we do this kind of registration without needing the entire volume? So when we look at something like point set registration, if we kind of gloss over the whole imaging side, can we somehow think of the images as point sets and compute some kind of spatial transformation that optimally registers our source, which in this case would be one of the images, to the other set of imaging, and we can often parameterize these kinds of geometric transformations, whether they're rigid or non-rigid, in some form of way. And there are lots of algorithms, things that many of you will likely have heard of, like iterative closest point, or ICP, which use some sort of iterative optimization process. But what we want to try and do is basically, the main issue with those kinds of iterative optimizations is that they're time consuming and they're not really ideal for real-time applications. We overlook some of those constraints. Can we construct some sort of learning-based approach, which doesn't require any iterative refinement and can sort of give us a one-shot registration that we could then use to apply to these imaging. So in our case, we want to use some sort of learning-based point set registration method that we could use the 3D point sets that are taken from some automatic, well-validated learning-based MRI and ultrasound segmentation tools that we could then use to do some form of rapid registration on the fly using potentially very sparse data to avoid needing an entire 3D ultrasound volume in the operating room. So what we came up with was what we've called the free point transformer network. So as I said, it's a learning-based method which computes non-rigid registrations and doesn't sort of at this time really require any explicit parametric deformation model like a thin plate spline or a rotation matrix or anything like that. Given its one-shot nature, we sort of get away from that iterative optimization process as we just directly predict the point displacements. And so we have two modules. And so the first one leverages something that's become quite famous in point cloud representation and embedding and those things, and it's called PointNet, which you can see over here. And sorry, I don't know if what's in the chat is for me. It's just not coming up on my screen.
No, it's fine. Keep going. Your voice is fading occasionally here and there, but it's not a huge deal. It's okay.
Okay, I'll move a little closer.
Yeah, exactly. If you're going to stay a bit closer.
Okay, great.
That'd be great. Yeah, thanks.
Okay, hopefully this is a bit better. Yeah, so what we have on the left side of the network, if you can see my mouse circling here, is the PointNet, which essentially takes in a series of points and converts them into a feature vector. And what we're then able to do is take the features from both our source prostate and target prostate and basically combine them and feed them into the second half of our network, which is basically at a high level just a multi-layer perceptron that's implemented as a series of convolutions across each of the individual points that are actually in inside of the prostate data. And we wind up with basically what you see over here, which is a set of transformed points. So we've taken this red point cloud over here, which we want to register to this yellow point cloud, and we wind up with this green one here. So what we actually have done, and I think a lot of people have alluded to this problem within imaging and within deep learning, is that we just don't have a lot of data. And so while we did have, like you can see here, and I'll mention in a second, 108 pairs of images, we found that just really wasn't enough for this network to sort of handle this problem well on its own. So we pre-trained with what appears to be sort of a very commonly used network or data set for training with point clouds, which is called ModelNet 40, and it's 12,000 unique different shapes. It's lots of tables, chairs, desks, like you can see up here. And we do some on-the-fly augmentation where we add deformation, rotation, and translation to these, and we give the network basically the task of predicting those displacements. We then fine-tuned with half of the prostate data set that we have, and then tested on the other, and just a little bit more information that's out there for those curious. So the first task we wanted to do was, well, what if we use the entire surface from the transrectal ultrasound, and we use the entire surface segmented from an MRI. And what you can see here, I won't talk about all of these, but sort of the most salient ones are over here, which are D and H. So as we're trying to register our source points here, which is B, being the MRI image, onto A, which is our ultrasound, up here we have coherent point drift, which is a sort of very well-known non-rigid deformation and an iterative optimization algorithm. And then you've got down here in H, which is our network after fine-tuning with prostate data. And you can see those are really the only two that kind of get close to the shape. And so we thought, well, this is good. But if we really wanted to avoid needing that entire ultrasound volume, what if we really only use two of the images from the transrectal ultrasound probe? So you can kind of just see it here. It's a little bit faint. Sorry about that. But you've got the probe here, and you could imagine the patient's prostate here in pink, and you've got 2 planes of ultrasound. And so you've got one, which is shown here if you're looking straight down through the probe, where you've got actually through, and you've got the sagittal view that you've got here at the same time. And so when we actually look at what that looks like on the data, you can see you basically get this one ring and then this other contour over here. And so our sort of real question was, well, what happens if we try and register this entire surface from the MRI, because we can do that before the procedure with this one snapshot from the transorbital ultrasound probe. And what you can see here is basically all the other methods kind of fall apart. Coherent point drift really doesn't handle well either, but our method still kind of maintains the shape of prostate overall when we try and register, again, the MRI onto the ultrasound images. So just some numerical results as well. So when we're looking at registering to the full ultrasound, we can see in terms of time, we're doing quite well. And these are just some of the other methods that I kind of glossed over. I'm happy to talk about them more if anybody has questions. But when we look at things like the Hausdorff distance and registration error of landmarks that were annotated in the ultrasound and the MRI, we tend to be either the sort of top performer or close to it. Chamfer distance here is quite similar to the mean square error, where it is the average distance to the nearest neighbor in the other point set. And what we've got down here is our results. Excuse me, when we've got just the 2 planes of points basically extracted from the imaging there. So while these numbers are quite great, it's good that we're ahead. It's another thing to note that when you look at conventional imaging methods, they often tend to have TREs somewhere in the range of about 1.5 to 3.5 millimeters. So when we look at the TRE here, you notice that that's maybe not quite as good as what we could have hoped for. But a lot of this is due in part to the fact that they've got not just the surface, but they also have the entire imaging data. Whereas here, we've really only just got these 2 lines of points really to work with. And using just this geometric and spatial information, we can really use next to no amount of data compared to an entire image volume and still be able to have sort of a fairly successful registration from basically an instantaneously acquired ultrasound slice. So it's also unclear as to whether or not sort of traditional image or intensity-based methods would be able to perform with this sort of lack of data that we've been able to leverage here for making use of our network. So just to summarize and sort of go through everything one more last little time, we were able to use the free point transformer, or what we call FBT, to produce those point displacements that are purely from geometric information that we get from prostate contours, and it improves on, or it's comparable to some existing methods that are used for registration that are done in sort of this non-trivial MR to ultrasound fusion task. And we found that it was quite effective with highly sparse point sets relative to basically all the other methods that we had tried and investigated. And given its ability to operate quickly, we're hopeful that something like this might be possible to use to perform continually real-time updating registration in an operating suite. And so with that, I'm happy to take any questions and just like to acknowledge funding for this project. And thank you guys for listening.